Welcome to our third mini lecture on peptide sequencing. You're probably going to want to print out a copy of this table of amino acid residue masses, unless you have a dual monitor, and throw it on your other monitor. I'd like to point your attention to the middle of the chart and look for glycine, weighs 57. Today we'll be pretending everything in our peptide that we're going to work with is glycine. Now, the first thing you have to remember about peptide sequencing, and these peptides I'm showing here, they're not exactly perfect. Sometimes I'm missing a proton. The point isn't to count everything perfectly. It's to illustrate this. We heat this peptide in the gas phase by hitting it with lots of neutral molecules. It excites vibrationally and the proton moves around, and depending on where the proton ends up, you get cleavage. Now, if you hit here, you get a B1 and a Y3, as long as, for example, we tend to use trypsin, and trypsin will leave a positively charged lysine on the C terminus, which is great. So our B ion will have a charge, and our Y ion will have a charge from this basic amino acid. So I'm not showing the charge that's on the lysine. You'll just take it for granted that it's there. But the peaks that you see in MSMS are not sequential. It's not like you break a B1, you break it once to get B1 and Y3, and then you break the Y3 to get other stuff. That can happen, and they're called internal fragments, but they're pretty rare for peptides. What happens is this. You either hit here and make these. M, by the way, is the parent ion. Or you hit here and you make these, B2, Y2. Or you hit here and you make these. Now, all of these can happen. Remember, I showed you a few slides back that this proton is hopping all over. It's like a little thing of roulette. Where does the proton stop? Doom, da, doom, da, doom. Oh, no, it stops here. That bond will break, okay? So picture protons hopping all over the place, stopping wherever they will, like a roulette wheel, and making a particular set of fragments that are complementary. Let's do this with a generic tetrapeptide. Remember, we could hit here, and if we did, we'd make these. Or we could hit here, and make the B2 and the Y2. Or we could hit here, and make the B3 and the Y1. Now let's look at the masses of these. If, as I've said, everything is glycine, remember your B1 has that extra hydrogen. It's there from the beginning. Has a positive charge, and so you're like always trained. I see that it's going to be 58 mass to charge, and then when you subtract away the proton, when you deconvolute, it's 57 Daltons. Let's go to our Y ion. Well, if you really want to be technical, you have an extra proton, not an extra proton, excuse me, an extra hydrogen on your N terminus. So it weighs 58, not 57. It has then the next glycine weighs 57, and the next one weighs 57, and then hanging off the end you have OH. Now you're saying, why is it OH and not O-? Well, it turns out in mass spec we spray out of acidic solution, so we will have protonated that. That's why we sprayed out of this at a pH below the pKa of the carboxylic acid. We add all these up, it's 190 m over z. Now, if you add 190 m over z to 58 m over z, it's one more than your precursor mass m over z. Oh boy, that's weird, but that's the way it is, and that's because of this mechanism that when you see a B1 and a Y3, you shouldn't think of them being made from exactly the same process. Remember, the Y ion you should think of it as having stolen a proton from some B ion that then becomes a neutral. It's not the B ion you see. The B ions that you detect are the ones that didn't get their proton stolen, but somewhere along the way, though, some Y ions were stealing them. Let's keep that, think of it that way for simplicity. Now we look at our B2 ions. Well, the first glycine is 58, right? It has that extra hydrogen, but then we go to regular residue mass. You add 57 to that, and that's 115 m over z. If you want to know what it actually weighs, subtract away a proton, it's 114 m over z. Y2, you have 58 plus 57 plus 17, and that's 133. You could just add all the residue masses together and add water as well, which would be 18, but I'm being really specific here. B3, which is down here, 58, 57, 57 for 172 m over z. 58 plus 17, 76 m over z. And so, this is how spectra are made. You're seeing as these appear, so do the peaks. So break here, make these peaks. M again is the parent ion. Now we make B2 and Y2. Now we make B3 and Y1. When you're looking at spectra, I want you to think of it this way. Make sure that you're always saying, oh, I have some B's and I have some Y's, and oh, neat. And these are the actual masses. B1, 57. Now these are, we've subtracted away the proton. I put in Daltons here, but if this is a deconvoluted spectrum, that's what it would look like. That's where everything would be. So I hope that'll help you. You know, there's not a lot of great references for getting down to the nitty-gritty without spending 30 pages of reading. Hopefully this is a good shortcut for you to understand where these ions come from, because we're going to be working with them a lot. It really is the bread and butter of protein mass spectrometry.